Okay, let's just dive right into this explainer. We're taking this sometimes intimidating world of probability and breaking it down into something you can actually really use. Whether you're trying to figure out if you need an umbrella today, totally guessing on a multiple choice test, or throwing down chips on a blindingly bright casino table, the hidden math of chance is quite literally running our everyday lives. And today, we're going to make that math perfectly clear. Consider this ominous quote from one of our sources. Many a gambler has gone to a cold and lonely grave for failing to make the proper distinction between probability and statistics. Kind of dark, right? But it brilliantly sets the stakes here. Knowing the math behind chance isn't just some boring academic exercise, it's practically a matter of survival. Misunderstanding these numbers can literally cost you everything. So you gotta ask yourself, are the odds ever really in your favor? To figure that out, we're going to build your understanding of chance from the absolute ground up, almost like a Russian doll. We'll start small with a simple coin toss and build all the way up to a high-stakes casino table. Let's kick things off with Section 1, the basics of probability. At its core, probability is just a measure of how likely an event is to actually happen. Think of it like a sliding scale. On one end, you have 0, which means absolute impossibility. No way, never gonna happen. On the other end is 1, meaning total absolute certainty. Now, it doesn't guarantee exactly what will happen in one isolated moment, but it's an incredibly reliable guide for what to expect overall. Let's take a super simple example. If you toss a completely fair, unbiased coin, your chance of getting heads is exactly 1/2, or 0.5. Why? Well, because there are only two equally likely outcomes, right? Heads or tails. The golden rule to remember here is that the probability of an event is always the number of ways it can happen, divided by the total number of possible outcomes. To really speak the language of probabilitists, you just need a few basic terms under your belt. An experiment is any repeatable procedure, like throwing a die. An outcome is just a single possible result from that throw. Then you have the sample space, which is basically your entire universe of possible outcomes. So for a standard die, that's just the numbers 1 through 6. And finally, an event is the thing you're actually looking for. That could be rolling a specific number, like a 5, or a broader category, like rolling any even number.
Moving right along to Section 2, the rules of the game.
Okay, so here's where we introduce the addition rule. The crucial trick here is how we handle overlapping events. Let's look at a standard 52-card deck. If we want to find the probability of drawing a red card or a 7, we can't just take all 26 red cards and all 4 sevens and add them together. If we did that, we'd accidentally double count the 2 cards that are actually red 7s. You always have to subtract that overlap. So 26 plus 4 minus the 2 overlapping cards leaves us with exactly 28 out of 52 chances. Next up is the multiplication rule. Now, if events are perfectly independent, meaning one doesn't affect the other whatsoever, like 2 completely separate rolls of a die, you just multiply their individual fractions to find the chance of them both happening together. Let's say you want snake eyes. Getting a 1 on the first die is a 1 in 6 chance. Getting a 1 on the second die is also 1 in 6. Multiply those together and boom, your chance of rolling double ones is exactly 1 in 36. And this brings us to a really massive concept, the law of large numbers, which you might also know as the law of averages. Check this out. If you roll a die just 6 times, you might end up getting 3 ones. That's way higher than what we'd mathematically expect, right? Short-term experiments can give you wildly chaotic results, but if you roll it 60 times, that proportion starts to stabilize. By 600 rolls, that empirical frequency firmly approaches the true mathematical probability of 1 in 6. Basically, over the long run, chaotic reality always bends back to the cold, hard math. All right, Section 3, 3 types of probability. Let's layer on a little complexity and look at 3 distinct flavors of probability, keeping our deck of cards as an anchor. First is marginal probability. This is the simplest. It's just the isolated chance of an event. Like pulling a red card is 26 out of 52. Easy. Then we have joint probability, which looks for an intersection. Pulling a card that is both red and a 4 is just 2 out of 52. But conditional probability, this is where it gets super fascinating. What is the chance of pulling a 4 given that we already know we drew a red card? Notice how our denominator shrinks right down from 52 to 26 in that last step? Because we know the card is red for a fact, we can instantly eliminate the entire black half of the deck from our sample space.
Now for Section 4, understanding Bayes' theorem.
So, Bayes' theorem sounds incredibly intimidating, but honestly, it's basically just an elegant formula that lets us manipulate those conditional probabilities. It lets us work backward. This theorem is an absolute game changer for real-world diagnostics. It takes our initial baseline statistics and lets us update our beliefs the exact moment we get new evidence, like a fresh test result. Let's look at a very real medical example from our source material. Imagine a breast cancer screening where only 1% of the general population actually has the disease. And let's say the test is pretty good. It gives a true positive 90% of the time and a false positive only 8% of the time. Now, if a woman takes this test and it comes back positive, the immediate, completely natural reaction is utter panic, right? But thanks to Bayes' theorem, we discover a totally shocking mathematical reality. If that woman tests positive, the actual probability that she has cancer is only about 10%. I know, how is that logically possible? Well, think about the scale of it. That 8% false positive rate is being spread across a massive 99% of the population that is perfectly healthy. So that huge number of false alarms heavily outweighs the true positives caught in the tiny 1% who actually have the disease. It's this massive shift in perspective that literally only the math can reveal to you. Moving on to Section 5, Probability versus Statistics. We hear these two terms used interchangeably all the time, don't we? But the difference between a probabilist and a statistician is profound. The probabilist assumes an ideal world. They'll look at a pair of dice and say, okay, assuming these are fair, six-sided dice, I have exactly a 1 in 6 chance of crapping out. The statistician, on the other hand, entirely questions the world. They look at those exact same dice and say, well, I don't know if these are actually fair, so I'm going to record a bunch of rolls to test if they're loaded before I even sit down to play. So probability figures out the consequences of a perfectly ideal world, while statistics actually analyzes real-world data to see if that world is ideal in the first place. This split in thinking also highlights two major camps of mathematicians, frequentists and Bayesians. Throughout this explainer, we've mainly used the classic frequentist approach, looking at long-run objective averages. But it's super important to remember that the Bayesian approach is heavily used in modern analytics too. Bayesians actually incorporate subjective prior degrees of belief into their data, and they constantly update their worldview as new experiments happen. And finally, Section 6, the roulette reality check. For our grand finale, let's take literally everything we've learned and see exactly why you are mathematically guaranteed to lose your money at a roulette table. Okay, let's say your strategy is to bet $10 on the number 20 for every single spin until every single slot on that wheel has hit. Since there are numbers 1 through 36 plus a 0 and a double 0, it statistically takes 38 spins to hit every slot. At $10 a spin, your investment is $380 to play that whole cycle. But here is the trick. When you finally hit that number 20, the casino calculates your single payout as if there were only 36 slots. So your return? It's only $360. And this, right here, perfectly exposes the infamous house edge. The casino's illusion is that payouts are structured as if your chance of hitting a number is 1 in 36. But the reality is, because of those extra 0 and 00 green spaces, your true chance is actually 1 in 38. The casino pays you based on this fictional ideal world of 36 spaces, but they charge you based on the cold reality of 38 spaces. So the math leaves you right here, -$20. Thanks to the law of large numbers, if you sit there and play long enough, that hidden gap guarantees that you will slowly bleed exactly $20 for every complete statistical cycle of the roulette wheel. This is literally the reason why the best possible casino strategy is just stopping early if you happen to get lucky. Probability is absolutely everywhere. It dictates the survival rates of sea turtles laying massive amounts of eggs. It dictates the multi-billion-dollar profitability of casinos. And yeah, even your odds of passing a multiple-choice test if you walk in completely blind. So now that you truly know the mathematical rules of the game, are you going to make your choices based on an ideal world? Or are you actually going to look at the cold, hard statistics of reality?